Many students confuse atoms, elements, compounds, and mixtures. They're related, but they're not the same thing. Let's make the differences simple. An atom is the smallest unit of an element. It still has all the properties of that element. Everything around us is made of atoms. Hydrogen is one example of an atom. An element contains only one type of atom. Every particle is made from the same element. Oxygen gas is still an element because it's made of only oxygen atoms. A compound forms when different elements are chemically bonded together. The atoms always combine in a fixed ratio. Water is a great example. Every water molecule has 2 hydrogen atoms and 1 oxygen atom. A mixture is simply different substances combined together. They are not chemically bonded. The amount of each substance can change. Salt water is a common example of a mixture. Here's the easiest way to remember. One atom is an atom. One type of atom is an element. Different atoms chemically bonded make a compound. Different substances simply mixed together make a mixture. Filtration is a method used to separate an insoluble solid from a liquid. The process is simple. First, place the filter paper inside the funnel. Next, slowly pour the mixture into the funnel. The filter paper has tiny pores. These pores are large enough for the liquid to pass through, but too small for the solid particles. As the liquid passes through the filter paper, it collects in the flask below. This liquid is called the filtrate. The solid stays on the filter paper. This solid is called the residue. Filtration only works when the solid does not dissolve in the liquid. For example, sand and water can be separated by filtration, but salt water cannot because the salt dissolves completely in the water. Evaporation and recrystallization. This method is used to separate and purify a soluble solid. First, choose a solvent that can dissolve the solid. Next, heat the mixture until the solid dissolves completely. Any insoluble impurities are removed by filtration. Then, gently heat the solution again. Some of the solvent evaporates, making the solution more concentrated. Now let the solution cool slowly. As the temperature drops, the solubility decreases. Pure crystals begin to form. The crystals are collected by filtration. Finally, rinse the crystals with a small amount of cold solvent and let them dry. The result is pure crystals. This method works because solubility changes with temperature. Distillation is used to separate and collect a pure liquid from a mixture. First, the mixture is heated. The liquid with the lower boiling point evaporates first. The vapor travels into the condenser. Cold water flows through the condenser, cooling the vapor. The vapor then changes back into a liquid. This pure liquid is collected in the receiving flask. The substances with higher boiling points do not evaporate. They remain in the original flask. Distillation works because different substances have different boiling points. A common example is producing pure water from salt water. Reflux is used to heat a reaction mixture for a long time without losing the solvent. First, the reaction mixture is heated. As the solvent boils, vapor rises into the condenser. Cold water flows through the condenser and cools the vapor. The vapor changes back into a liquid. The liquid then drips back into the reaction flask. This cycle repeats continuously. Because the solvent always returns to the flask, none of it is lost. This allows the reaction to continue at the solvent's boiling point for an extended period. Unlike distillation, no liquid is collected in a separate flask. The purpose of reflux is to keep the reaction going while preventing the loss of solvent. A common use of reflux is in organic synthesis, where reactions often need to be heated for a long time. A separatory funnel is used to separate 2 immiscible liquids. These liquids do not mix together. First, add the mixture to the funnel. Close the stopper and shake it gently. Then, let the mixture stand until 2 layers form. The less dense liquid stays on the top. The more dense liquid settles at the bottom. Open the stopcock and drain the lower layer first. Then collect the upper layer in a separate container. This method separates liquids based on their different densities. The melting point is used to check the purity of a solid. A pure substance melts at a sharp and fixed temperature. An impure substance melts over a wider temperature range. First, place the sample into a melting point tube. Attach the tube next to a thermometer. Then place them into a heated oil bath. Heat the sample slowly. Record the temperature when melting begins and when it is complete. A narrow melting point range indicates a pure substance. A wide melting point range suggests that impurities are present. Paper chromatography is used to separate the different components of a mixture. First, place a small spot of the sample on the start line. Next, put the paper into a container with a small amount of solvent. The solvent must stay below the sample spot. As the solvent moves up the paper by capillary action, it carries the components with it. Each substance moves at a different speed. This happens because each substance has a different polarity. The paper is polar because it contains water trapped in the cellulose fibers. More polar substances are more strongly attracted to the paper. They move more slowly and travel a shorter distance. Less polar substances are more soluble in the solvent. They move faster and travel farther up the paper. When the solvent reaches near the top of the paper, remove the paper and let it dry. The separated spots can then be identified. We can also calculate the RF value by dividing the distance traveled by the substance by the distance traveled by the solvent front. Paper chromatography is commonly used to separate inks, food colorings, plant pigments, and amino acids. Everything around us is made of tiny particles. These particles are always moving. This idea is called the kinetic molecular theory. The faster the particles move, the more kinetic energy they have. Temperature is simply a measure of the average kinetic energy of these particles. At the same time, particles attract each other through intermolecular forces. The balance between particle energy and these attractive forces determines the state of matter. Let's compare the three states. In a solid, the particles are packed closely together. The attractive forces are very strong. The particles can only vibrate in fixed positions. That's why solids have a fixed shape and a fixed volume. In a liquid, the particles are still close together, but they have more kinetic energy. They can move past one another while remaining close. As a result, liquids have a fixed volume but take the shape of their container. In a gas, the particles have much more kinetic energy. They move rapidly in all directions and are far apart. The attractive forces become almost negligible. That's why gases have no fixed shape and no fixed volume. Now let's look at how matter changes from one state to another. When heat is added, particle energy increases. A solid melts into a liquid. A liquid boils or evaporates into a gas. When heat is removed, particle energy decreases. A gas condenses into a liquid. A liquid freezes into a solid. Some substances can even change directly between a solid and a gas. Solid to gas is called sublimation. Gas to solid is called deposition. The important point is that during every change of state, the particles themselves do not change. Only their energy, movement, and spacing change. Once you understand how particle energy competes with intermolecular forces, every change of state becomes much easier to understand. When heat is added to a substance, its particles gain energy. At first, the solid becomes warmer. The particles vibrate faster, so the temperature increases. Eventually, the substance reaches its melting point. At this stage, the temperature stays constant. The added energy is no longer increasing the temperature. Instead, it is used to overcome the intermolecular forces holding the particles together. This energy is called the enthalpy of fusion. Once all of the solid has melted, the liquid begins to warm up. The particles move faster and the temperature increases again. Eventually, the liquid reaches its boiling point. Once again, the temperature remains constant. The added energy is now used to separate the liquid particles completely and turn them into a gas. This energy is called the enthalpy of vaporization. After all of the liquid has become a gas, the temperature begins to rise again. The gas particles move even faster. The enthalpy of vaporization is always greater than the enthalpy of fusion. This is because turning a liquid into a gas requires much more energy than melting a solid. The heating curve follows a simple pattern. The temperature rises. It stays constant during melting. It rises again. It stays constant during boiling. Finally, it rises again after all the liquid has become a gas. This is how energy changes during a change of state. Not all particles in a substance move at the same speed. Some particles move slowly, while others move much faster. This range of particle speeds is described by the Maxwell-Boltzmann Distribution. At a lower temperature, most particles have relatively low kinetic energy. The distribution is taller and narrower. As the temperature increases, the average kinetic energy also increases. The entire distribution shifts to the right and becomes broader. Notice that the total area under the curve stays the same. This is because the total number of particles does not change. Only the distribution of their energies changes. Now look at the shaded area on the right side of the graph. These particles have enough energy to escape from the surface of a liquid. This process is called evaporation. As the temperature increases, a larger proportion of particles have enough energy to escape. That is why evaporation happens faster at higher temperatures. Temperature is directly related to the average kinetic energy of the particles. As the average kinetic energy increases, the temperature also increases. Remember that absolute temperature is measured in Kelvin. To convert degrees Celsius to Kelvin, simply add 273. For example, water freezes at 273 Kelvin and boils at 373 Kelvin. Evaporation and boiling are not the same process. Evaporation happens only at the surface of a liquid. It can occur at any temperature because some particles always have enough energy to escape. As more particles escape, they create vapor above the liquid. This vapor produces pressure, called vapor pressure. When temperature increases, particles have more kinetic energy. So more particles escape and the vapor pressure increases. Boiling happens when the vapor pressure of the liquid becomes equal to the external pressure. At this point, bubbles can form throughout the entire liquid. That is why boiling happens throughout the liquid, not just at the surface. At normal atmospheric pressure, water boils at 100 degrees Celsius. If the external pressure increases, the boiling point increases. If the external pressure decreases, the boiling point decreases. Intermolecular forces also affect boiling point. Stronger intermolecular forces make it harder for particles to escape, so the vapor pressure is lower and more heat is needed to boil the liquid. This means the boiling point is higher. Weaker intermolecular forces allow particles to escape more easily, so the boiling point is lower.